Hello, welcome to another lesson. So today we're going to continue on with the lessons on the transformation of functions. So last lesson, we basically set forward a framework to sketch and determine the transformations applied to certain functions. So the big three transformations that are in this topic are reflections, which we used to call flipping, and translations, which we used to call shifting, and dilations, which we used to call steepness or compression. So in this lesson, we'll just go through a few more questions and then see how the transformations work for trig functions, where the third lesson, which is 3 out of 3 lessons, we'll try to cover some past paper questions that we observed from both the New South Wales papers that trial papers that have been released this year, and also some of the Melbourne exam papers as well. So let's hit up the PowerPoint slides. So last lesson, we basically introduced an all-in-one formula, which I think it's pretty neat to sort of have it all down on paper, where the two black circles there represents the two reflections. So if you have a plus minus in front of the whole function itself, that basically reflects, if it's negative, it'll reflect about the x-axis. Similarly, if it's plus minus in front of or inside the function, in front of the x value, effectively, you will reflect it about the y-axis. The two green items represent the dilations, and the two red ones represent translation. So if you have forgotten what those components are and how they apply, refer to the last video. Otherwise, let's apply this now to a few questions. So the first question that I prepared is hopefully pretty straightforward, where we're just going to apply these transformations to an absolute value function, whereby you can see there that the gx function there has a number of transformations. Let's unpick it. So there's a 2 there, -4 there, and maybe a +9 outside of the function. So that 2 there is a vertical dilation effect. That -4 inside the function would obviously be a horizontal translation. So I'm just going to identify it, and then I'll list out what the word it actually is in full wording as part of my answer. So +9 outside the function is obviously a vertical translation or a shift. Now, I mentioned in last week's framework that in the absence of any guidance, there's a certain pecking order or certain priority list that we should go down the path of. It doesn't always have to be like this, right? You can mix it up, and some questions that I'll show you next week do mix it up from the start and just causes the transformations to be a bit weird. But if you remember this order, you generally get it right. So, and that order was reflections first, and then your verticals, and then your horizontals. Now, the vertical and horizontal order doesn't matter, but I always start with vertical and horizontals. But more importantly, within verticals and horizontals, for that matter, it's always dilation and then translation. So let's go with that. So there's no reflections here, right? So everything's in positive land. So I'll start with my verticals. Vertical, and there's 2 verticals, so I'll start with dilation by factor 2, or of 2, and maybe of 2 is a better for English. And vertical translate. Now, upwards, right? +9, upwards by 9. And then horizontal translation. If it's a -4 there, it goes to the right. So horizontally translate or translation to the right by 4. And that's my answer. So nothing too wow about that question. I just thought we'd start in a place that connects with last week's framework. So pretty straightforward there, nothing too fancy. Let's do another one. So in this one, we're transforming an exponential function. That's my original to gx, which is looking like that. So once again, unpicking the transformations at play, you can see there's a minus in front. That's a reflection. Now, if it's in front of the function there, it's safe to say vertical. Oh, sorry, not vertical. It's a reflection. Technically, it is a vertical reflection, but reflection about x-axis would be a better way to describe it. Now, where would the reflection be if it was reflecting on the y-axis? It'd be the negative would be in front of the x inside the function, which is upstairs. But in this case, there's no negative, so no reflection there, but there is a -2 inside the function, so that's a horizontal. We shift the left and right, eh? Horizontal translation. And then there's a +4, which is a vertical translation. So this one here is pretty straightforward. The order is less important because actually you can put the reflection, put the reflection first, and then the translations. Doesn't matter which order you put it in, it's equally fine. But we'll go with our framework of our pecking order of doing the vertical before horizontal. So reflection about the x-axis, and then vertical translation upwards by 4, and then horizontal translation -2, so to the right by 2. Once again, nothing too hard about that, hopefully. Pretty straightforward, I say. Yeah, pretty straightforward. Yeah, 2 relatively easy questions just to get our gears working, right? So let's move on to a third question before I do a bit of theory on trig. Now, this is a classic question. So this used to be in the old syllabus, right? Where you basically get given a parabola that's in the function, a general function of ax squared plus bx plus c. And they get you to transform this into this one. So we're given a question that has a general form, and then they want it in the sort of factorized vertex or standard form. Sorry, not standard form, vertex form. Standard form in the old syllabus means something else. All right, that's no longer in the syllabus. So it looks like we're gonna just factorize a 2 and then complete the square and see where it takes us. Find the values of, and have the values a, b, c being constant. We then sketch, and then transformations made to x squared. Okay, perfect. So for part A, we start off with our function looking like 2x squared minus 8x minus 12. And to transform it into this format, firstly, smart thing to do, factorize a 2 out. And then I'm just going to leave a bit of space in between here so I can add and minus numbers to complete the square. Now, to complete the square, it's basically half of -8 squared, so half of -8 is -4, 16. And then simultaneously minus 16, so you don't change your question. So this here is my perfect square. So that is 2x minus 4 all squared. And then you combine these two numbers together to give you what, -28. Yeah, that looks big. Let me just check. Oh, I did that wrong. So let me go back, because when I factorized the 2 out, I didn't factorize the 2 out. For these guys, that's naughty. It's good for me to pick up things like that. So that's 4 there, and that's a 6 there actually, which means to complete the square, it's not 16, is it? Let's see, it's 4, and then -4, and there's a plus missing. Oh, sorry, a minus missing. Make sure the mass is now right. Yep, don't want to go forward with something that is needs to be adjusted. So that looks fine. So factorize, perfect. So then once again, this guy here is a perfect square. That guy there is, well, grouped together as a constant. So x minus 2 all squared, and that's minus 10. And then maybe just expand that using rainbows, and you get your expression looking like minus 20. Let me just make sure 6. Yeah. Yep. So therefore, that's my answer there. Let me put a nice pretty box around it. Highlight. All right. So that's basically the factorization now. And that, I mean, it will ask me to sketch it, and then the transformation made comes off the back of that. So technically A and B are not new. Old syllabus questions had those. It's part C that describes the transformations. That's new syllabus. So the sketch itself, I mean, the vertex is 2, -20. So maybe I'll draw my number plane with that in mind, where I know it's going to be very negative. And the y-intercept, if you look at initially it's 1 still. So without sort of putting in too many features, I know that the x value is 2 and the y value for the vertex is -20. That's the beauty of having it in this format. And then you basically sketch yourself a parabola, not to scale, of course, where I know this is -12. I'm going to leave it there, right? If it doesn't ask you to do the x-intercepts, I mean, you can, right? Yeah, you can solve. Let me see if it's nice. If I factorize that. Yeah, it's nice, is it? No, it's plus minus root 10. So basically, if you solve that there, you can get it technically to be, if you set that to 0 and solve it, you get, was it 2 plus root 10 and 2 minus root 10? Yeah, I'm just solving this bracket here. So you can get it, right? It's probably not necessary, probably a bit of an overkill point, but there it is. So I'm just going to label everything, right? And there's my vertex there. Perfect. Because it basically shifts to the right and then shifts down by -20. So part B, very easy. I guess it's similar to what we've done in the old syllabus. Now, I guess you're all here for part C as opposed to anything. So the transformations that take me from y equals to x squared to this transformed function of, what's that? There's a 2 in front. X minus 2 all squared minus 20. So once again, let's unpick this quickly. There is a vertical dilation. And once again, how do you know that's vertical? Well, it's, if you can, when you rearrange it, technically it can be on the other side, right? And it's multiplying in front of a function. If this was inside the function and multiplying with x, then it's a horizontal dilation. Yep. So that minus 2 is inside the function, so that's horizontal translation. And that minus 20 is outside, so that's a shifting up and down, which is a vertical translation. So putting those in words, got 2 verticals and a horizontal. I'll start with my vertical, and it's very important for you to start with a dilation. It's a vertical dilation or stretch, right? Because it's bigger than 1 by factor of 2. And then you got a vertical translation. Now, -20, so downwards by 20. And last but not least, you got a horizontal translation, shift in the old syllabus speak. Now 2 units minus 2 there, so to the right by 2. And that's it, guys. Nothing too hard about that, hopefully. Yeah, just thought I'd give you a question where you do need to complete the square a bit and manipulate it from a general form version of a parabola to a vertex form, right? So there are 3 quick examples that relate to the framework that we set up last week for transforming functions. Now let's look at trig functions and transforming those. So nothing too new about it. The only new concept is this concept of phase, but that's really easy anyway. But I thought for completeness, let's do some trig functions here. So with trig functions, I'm going to do something very similar to what I've done already, and that's basically, so maybe I'll call that first point 1, and this is number 2, so trig functions. My classes know that I'm absolutely poor when it comes to remembering the numbers for headings. I always get it wrong, and yeah, there you go, a bit of peek behind the curtain there. So I'll give point I under this, where let's give a all-in-one formula for trig specifically now, and I'll use trig constants and numbering just to make it consistent. So if I sketch a trig graph, right? So there's always or can be a plus minus, and A is in front instead of any other letter because that's amplitude, right? Which for the purposes of trig functions, amplitude is dilation, right? It's the stretchiness vertical dilation to be specific, right? So amplitude and vertical dilation is the same thing. Yeah? Sine or cos or tan for that matter. And if I open this bracket, now technically there can be a plus minus here as well. You rarely see minuses in there. Sometimes you do, and that basically changes the flipping or the reflection about the y-axis. And then the letter of choice is n, because n is used for period of motion, right? And then you have x minus b. Yep, very similar, and then plus c. So in terms of functionality, it looks exactly the same as what we've done before, right? So let's highlight the ones that we are. Now I'm just gonna shift this down a bit so that I have a bit of space on top so I can write my all-in-one. So this one here, obviously is reflection about the y-axis, no, x-axis. And similarly, this guy here is reflection about y-axis. And then I'd like to highlight for A, this is A is amplitude, but also in terms of the transformation, it is a vertical dilation. Yeah, similarly, N, right, is the period of motion, which it compresses or stretches horizontally. So the period is defined as 2 pi on n, right? That's where n is actually used. So n is the period component or frequency, some might call it, but it's representing horizontal dilation. And last but not least, I'll change colored pens for this. The two red ones there and there are translations. So this one here will be horizontal if it's inside the function, horizontal translation. And this one here, vertical translation. So that will shift your trig graphs up and down, and the previous one left and right. All right, so that's an all-in-one form. I guess before I go on, just to capture a graph for trig. So if I had a trig graph that shifted up and down, now that plus C, I call it equilibrium, because basically the wave graphs oscillate around that equilibrium. Some teachers call it the center of motion, whatever you want to call it. You basically have a trig graph that continues to oscillate around that point where this might be your C. And just to be clear there, so I'll use green again because I've used green upstairs for it. That there is your amplitude, and which makes from this point here to this point here one full wavelength. So the period of motion is equal to 2 pi on n, right? And just to note, for tan graphs, the period of motion is only pi on n, right? So because each wavelength is only pi here. So that's a sample of the trig graph amplitude and period is the two most commonly asked things. I've noted in some of the past papers that I've gotten all the trials, the other thing that teachers started asking is this concept of phase. So that seems to be a new buzzword for trig graphs. Phase is so easy. So if you define or understand that the definition for phase is just the horizontal translation, right? It is, that's it, right? That's phase, yeah. So actually, on your diagram, might be worthwhile to put in that component there is phase, right? So two quick examples. If I had y equals to sine x minus pi on 2, right? That's shifting the graph to the right by pi on 2, then phase would equal to pi on 2. Yeah, and similarly, if y equals to cos, now I'll do one that says 2x plus pi on 6. Be careful here. Whenever that's a 2, before we determine how left and right it shifts, smart thing to do would be to factorize the 2 out to actually ascertain what your phase is or what your shifting is, right? So in that case, their phase is equal to negative pi on 3. Yeah, so the order of horizontal dilation and horizontal translation is clearly drawn out here, because before you actually sketch this graph does not just merely shift over left and right by minus pi on 6. You have to factorize it out so it looks in this form, so you know what the phase is. So just keep that. Oh, it's not even pi on 6, is it? So it's actually 12, isn't it? Yeah, because I'm halving it a bit more, so I'm just going to put in the 12 there and 12 there. Just be careful with that, right? So we don't determine the phase based on the original expression. Force factorize the 2 out, so it becomes pi on 12. And that's negative because that's a plus pi on 12. Let's do some questions. So I've only got one question with 3 subparts left for this lesson, but hopefully that gives you a good good overview of what involves with transformations for trig functions. So let's have a look at this. So for the following, I want to transform fx to gx. There are 3 examples that I think get readily more involved as we go on, but not too hard. So I'm going sine, cos, sine, and transforming those into the same sort of functions, but slightly more complicated. So the first one that I have goes from fx of sine, and it transforms into gx, 3 sine x minus 4. So nothing too wow there, and I'll use my green pen to basically unpick this. So there's a 3 and there's a minus 4. Just to be clear, that one there is a vertical, that's amplitude, right? So that's vertical. I got a state, sorry, I should highlight that, state. So list of transformations, state the amplitude and period. Okay. I should read the question, right? Vertical dilation, aka amplitude, and that is because it's outside, that's a vertical translation. So the order there matters, right? They do not commute. In other words, I would always do dilation before I do translation. Yeah? So when you do this, your transformation should be vertical. Let's make sure that's the case. Vertical, yep, vertical dilation of 3, and then by a factor of 3, maybe by factor of 3. And then, by the way, sometimes whenever, instead of using the word vertical dilation, sometimes the language used is, it's a dilation from the, because it's vertical, it's from the x-axis. So whenever you see like, it's a stretch from the x-axis or from the y-axis, from the y, it's horizontal, from the x is vertical. So just to cover that point, just in case you see that and you're like, well, I've never seen a dilation relative to an x-axis. And then last but not least, they're vertical translation. Now, -4, so downwards. That's our equilibrium shifting, downwards by 4. All right. So that takes care of the transformations, and I'll put a box around that, but that's not the entire question there, is it? Just to close it off, amplitude is the number in front there, that's 3. And the period of motion is 2 pi. There's no number in front of x, so that's just 1, so that's just 2 pi. Yeah, that's a piece of cake, done. So, part B. fx equal to cos getting transformed into gx cos, oops, no equal sign, cos of x minus pi4 minus 2. All right, let's unpick this. So there's no amplitude difference, so amplitude is 1. There is a horizontal translation and something that will be a vertical translation. So two translations where the order really doesn't matter, right? When it comes to two translations, I always do vertical first. So let's go there. Vertical translation. Now, vertically, it goes down. So the equilibrium goes down by 2. And horizontally, translates. Now, minus pi4, so to the right, by pi4. So nothing too hard about that, right? Normally, these questions would probably be accompanied by a question that says sketch, right? And sketching trig graphs is an art in itself, so hopefully you guys are on top of that. So the amplitude there is 1, and the period of motion. Now, there is no component in front of x, no constant, so it's still 2 pi on 1, which is 2 pi. Pretty straightforward, and that's done. Now, the last one, where we're basically transforming sine x into gx, which is 5 sine, oh, this one is a bit more involved. So that's a 2x plus pi, and then plus 1 as well. Now, like I said before you actually do anything, it might be worthwhile to force factorize the 2 out and re-express gx as sine 2 outside of x plus, because you're force factorizing 2 from that, it becomes pi on 2 plus 1. And now we unpick. So I'm just going to shift this over a bit so I have a bit of space to do my little notes. So I've got 1, 2, 3, 4. So once again, I might borrow a bit of vertical space to do so. And I've got heaps of space now, so it's perfect. All right, so that guy there is amplitude or vertical dilation. There's a 2 there, which says horizontal dilation. So that is a stretch, stretching horizontally, right? Actually, no, I lie. It is not. It's basically halving it. So basically it's compression, right? And we know that because 2x basically means I fit 2 sine graphs into the 2 pi range, which in our case, the period is halved. There's a plus pi on 2, which basically means I'm shifting to the left. horizontally, so horizontal translation component. And last but not least, there's a vertical translator. Now, there are 4 there. So like I said, the order for vertical versus horizontal really doesn't matter, but within horizontal and vertical, dilation should come first. So vertical dilation by factor of 5. I can see that there. And then vertically shifts up. The equilibrium shifts up. Translation upwards by 1. Horizontally dilates. Horizontal dilation in this case is compression. So you can say compression by factor of 2. Same thing. Dilation by factor of 2. Last but not least, horizontal translation. Let's see, translation by, or to the left by pi on 2. Yep. So I think sketching this guy is actually quite complicated and involved. Maybe I'll do a future video on that. It's not easy, right? Sketching trig graphs like this. So let me close out this question though. Amplitude. So I don't need a dot there. Amplitude is 5, and the period of motion is 2 pi on the number in front of x, which in this case is 2, so it's just pi. That's a tick. So hopefully that gives you a flavor of the transformations of trig functions, where it's exactly the same as what we used to do with amplitude, period, and shifting the center and squashing the compression of trig graphs, etc. The only new thing is, and maybe I should have, if they ever ask you for this one, it's not, but basically for each one of these questions, if they ask for the phase for this one, there is no, so 0, right? There is no horizontal translation. Phase for this one, horizontally translate, so it's pi on 4. And phase for this one, if they ever ask that, it's negative pi on 2. So it's not too hard, it's just a horizontal translation, and that's the new component for trig functions. So hopefully that video was useful. If you like that video, can you please give me a like and a subscribe, send it to your friends if they're in need of a bit of theory on transformation of functions. So next video, we're going to do some past paper questions on this topic, and yeah, wrap that up. Thank you. See you guys later.